Welcome everyone to this session on PSI homomorphic encryption. The first talk is on blazing fast PSI. This is joint work with Peter Rindal, Srinivasan Raghudaman, and Philip Shopman. And Peter will do the talk.
All right, thank you. Yeah, we'll be talking about private set intersection. This is a classic MPC problem where Alice and Bob each hold a set X and Y, and they want to identify the intersection of their sets without revealing the items outside the intersection to the other party. And in this formulation of the problem, we have like a sender and then a receiver. In this case, Bob, and only Bob should learn the intersection, and the sender should learn nothing from the interaction other than some like basic data like the size of the sets. PSI is far from new. Probably the first PSI protocol dates back to '82, where Meadows first described the basic idea of doing PSI using Diffie-Hellman. There've been like many works since this, and then sort of culminating in 2010 with like a malicious skier protocol. Then there was sort of a fundamental shift where we went from public key cryptography to symmetric key cryptography, specifically OT extension. This was the work done by Pincus, Schneider, and Zoner in 2014. And then there was a series of works that continued to improve the running time of the protocols. So this here is shown communication on the y-axis and running time on x in log scale. So these are quite big jumps in terms of running time, but the communication sort of stayed steady, maybe a little worse. In addition to these semi-honest protocols in around 2017, there was a couple malicious secure protocols also based on OT extension, but the gap remained sort of big between the two in terms of performance. And then in 2019, Pincus and friends came up with this really clever idea to modify OT extension, sort of the internal nuts and bolts of it, and they got really low communication overhead, beating the Diffie-Hellman approach. But this came at a sort of large hit performance, and but fortunately, there's sort of several follow-up works that refined the ideas and introduced some new data structures, in particular, a data structure that's referred to as OKBS. And in our work, we take these some of these new ideas, and in addition, apply I'd say the favorite newish primitive of this workshop is Vole to get a very fast PSI protocol. So it's both very fast and also very low communication overhead. So today I'll be talking about how that is done. Our starting point is arguably the simplest PSI protocol. So we have each of the parties has a set X and Y, and the first thing we do is have the sender sample a PRF F, and then they run a protocol known as an OPRF, Oblivious PRF protocol, and this protocol allows the receiver with their set Y to input their set and get PRF evaluations of each of their set elements. You can think of this as sort of like we're encoding the sets under the PRF. And then the PSI can complete by just having the sender encode their set X under their PRF and send this over. And then you can compute the intersection of the encoded sets. And then from that, you can sort of easily infer the intersection of the original sets. And the receiver doesn't know what the PRF is. They just have the PRF evaluations. And that's sort of the security that you get from the Oblivious PRF. So it's a pretty simple protocol, and basically all PSI protocols follow this rough outline. Each one has its twist on it, but this is the basic outline. And in fact, our protocol sort of exactly matches this. And one of our core contributions is like, how do you implement this OPRF very efficiently? As a point of comparison, I wanted to introduce at high level, how the PSC and KKRT protocols work. These were the first ones to be based on, or some of the first to be based on Oblivious transfer extension. And they introduced a primitive that is referred to as a bark OPRF. This is sort of like a low grade OPRF in that you don't get to input one PRF and have the receiver set evaluated on it. Instead, you must input n different PRFs, and then the receiver gets one evaluation per PRF. And this sort of, I mean, we're encoding it under the PRF, so we still get all the PRF security, but then you have an issue in that what should you send in this last message? What should the sender's encodings be, right? There's no longer one PRF to encode your whole set under. Sort of a trivial and not very satisfying solution would be to encode your set of size n under all n PRFs. This would get you correctness, but of course this is quadratic overhead, and we want to run PSI of like 1 million items, so not doable. One of the core contributions of the PSC protocol is to introduce this idea of cuckoo hashing. It's basically a clever way to arrange your set in a certain way, which helps you get around this n squared overhead. And I'm not going to go into the details, but suffice it to say that you no longer need to encode under all possible PRF keys. Instead, they give you like these hash functions which index three of them, and you only need to encode each of your X items under 3 possible choices. So the main takeaway here is that like this protocol is relatively efficient. You know, the Bark OPRF is basically a fancy OT extension, and then you have to send 3 encodings per. So there's not too much here that's inefficient, but this is what we have to compete with. So as I'd mentioned, our starting point is not OT extension itself, but instead vector OLE. And yeah, as we've seen several times this workshop, Vole is basically can be viewed as the parties getting a secret sharing of scalar delta times a vector A. And here we're over like a 128-bit field, something decently large. And in particular, we're going to use the silent PCG based constructions that like Lisa was talking about. And this allows us to sort of run a very small setup phase, output these distinct keys, and then locally expand them. And this whole process is, due to like the recent improvements, is like very efficient. So this is how we start. Okay, we have our Vole correlations, but now we want to do PSI. How do we do this? So as a way of like a warm-up, introducing you to the ideas, consider for like explanation, let's assume that this A vector, which is supposed to be uniformly random over the the space of it, but what if we could imagine that at the indices indexed by the set Y, that this A vector happens to be 0. If this was the case, then it's not hard to see from the Vole correlation that this B vector and the A vector will be equal precisely at the locations that are indexed by the set Y, and at all other locations the B and C vectors will differ by some multiple of delta. So we can define our OPRF as just f of x equals b sub x, and send over the encodings as this shown here. And then, the receiver can encode their set by just, again, indexing their positions of C. And for the items in the intersection, these encodings will be equal to each other. And for all items outside the intersection, the x's will be off by some delta term. And so one issue that I sort of glossed over here, is A is supposed to be uniformly random over like the large field, but we need it to be 0 precisely at the slots indexed by the set to Y. And this then is not an issue. We can just the idea is you just send like the difference between the vector you have and the vector you want, and you de-randomize A to be your choice. So this requires communication, but it's like very concretely efficient at this. The second, and maybe arguably much bigger issue, is that we need these the domain of the sets X and Y to be relatively small so that we can use them as indices into these vectors. These vectors are, they're big, but they're not exponentially big. So how do we allow our set strings to be large without incurring exponential overhead? And to see how we're going to do this, let's sort of just reformulate what we're doing here a little bit. Right, our PRF of x is just b sub x. An equivalent way of saying this is the PRF of x is the inner product of b and this unit vector, which is 1 precisely at index x. So that's right, the same thing. And then that's sort of further abstracted away. Instead of explicitly writing this unit vector, let's just call it a function rho sub x. So we're just taking it, our PRF is just the inner product of b with rho sub x. In the real construction, we actually need to do an additional step of hashing this to destroy some linear correlations, but let's ignore that. All right, so using our new sort of vector inner product notation, right, the computations that we want to do is the sender will do inner product of x and b, the receiver will do inner product of rho y and c, and then also needs to ensure that a inner product rho sub y is equal to 0. So that's what we had just explained. And formulating it like this sort of hints at how we could get around this small domain problem. And instead of restricting the rho function to be outputting unit vectors, we can allow the rho function to output, higher weight vectors over the full domain. And in fact, based on how we choose the distribution of rho, we can actually get sort of like very different constructions with different properties. And we'll talk about some of the options next. So yeah, overall, right, our main computation is as follows. For the sender compute their OPRF outputs, they construct this matrix with all the rows in it. Then they'll do matrix vector multiply. Similarly, the receiver will construct their matrix and do their matrix operations to get the desired correlations. Let's zoom in on the receiver. Right, and that's for ease of explanation, let's rename this matrix to M. And so, right, they need to do two things, compute M times C, and then solve for A such that M times A equals 0. The way I presented it so far, right, we wanted to say M times A equals 0, but this actually ends up being somewhat problematic because you can choose A just to be 0. And will violate some security issues. So we'll in fact need M times A to be equal to some special value V. Don't really want to get into the details, but you can think of V as like 0 if you want. But in general, it'll be some special values here. And so equivalent way to say we want to solve for A is to say we want to compute M inverse times V and set that as A. And so we want these two operations to be efficient. M times C, we need it to be fast, and then M inverse times V should also be fast. And the question is, how do we do this? And then there's also a third requirement that we care about is that we want the dimensions of this matrix to be roughly square. The more stretched out it is, the easier it is to invert. But when we de-randomize A, we have to send a vector of size A. So the more stretched out this matrix is, we'll get less good communication overhead. So our first, and maybe, I don't know, maybe simplest approach is actually to use polynomial interpolation. So to see how this works is we'll define rho of x as just outputting the powers of x. This will be the vector. And then when we plug it in, right, the matrix will just look like all the powers of y shown here. And so the matrix vector multiplication is actually just exactly polynomial evaluation. And then for interpolation, or for the inverse operation is then just matrix polynomial interpolation, which is basically filling out this matrix with the Lagrange coefficients. And so, as I'm sure most people know, the performance of this, I mean, if you implement it right, you can get n log n for the matrix multiply and n log n for the polynomial interpolation, which is, it's pretty fast, but if you're in the game of PSI, you don't like logs. one really nice thing about polynomial interpolation is that the matrix is exactly square. So you're getting a really tight encoding, but you're paying for it in with this log overhead in terms of running time. So in this work, we present like a new approach. Well, it's not really new. Mike and friends had sort of first introduced this idea, and we sort of improve on it. And the idea is that we're going to define this row function as a binary vector, and they're going to be random, subject to the constraint that each row vector is weight 3. So example, row 42 could look like this, who knows? And the idea is that matrix multiply is quite easy to see that it'll be quite efficient because M is very, very sparse. And so you're just gonna, for each element, you just add up 3 spots in C. That's easy. The more tricky one is to show that you can in fact invert this matrix in linear time, and then I guess more generally that an inverse even exists. Like this matrix might not be invertible, so we need to ensure that this is the case. And to do this, we show that if you set the sort of the ratio between the height and width of the matrix to be 1.2, then with overwhelming probability, the matrix is invertible. And then, as we'll show, that our algorithm will in fact find this way to invert it in linear time.
So that's overwhelming in N?
What?
Overwhelming in N? I mean, do you need N to be very large for this?
Yeah. There's
the 1.2 is a function of N, no?
1.2. So we mostly care about when N is like 100,000 or,
okay.
Yeah, when it gets small, there's like, but yeah, we actually compute parameters for small N too, but this is when N gets big. So what's going on here? Let's take this guy as an example. Right, each row corresponds to some input set element, and now we want to invert this. And the basic idea, very common in sparse systems, is that you want to rearrange the matrix to be triangular. And once it's triangular, it's very easy to invert. You just do the backpropagation algorithm. And so then the question is, how do we triangulate this matrix in linear time? And the algorithm is actually relatively simple. That wasn't necessarily the hard part. The one way to see how the algorithm works is that you can view it as a graph problem or a hypergraph problem. So the correlation between these two is that for each column of the matrix, we'll have a vertex. So vertex 1 through 6. And then each row of the matrix will correspond to a hyperedge. And the way you can triangulate these matrices is that you look for vertices with degree 1. And then you, so for example, we have vertex 2 with edge A, so it has degree 1. And so the idea is that you iteratively delete these vertices. So we delete that guy, and now we look again in the graph for a vertex of degree 1, and 5B is 1, so we can delete that guy, and we recurse and delete all the edges. So this gives us a list of vertice edges that we've been deleted, and this list is precisely the coordinates of the ones on the diagonal. So starting from the bottom left is like 2A, 5B, and so forth. So that's how, in this algorithm in general, is called peeling. One issue with this algorithm is, say we run it again for some other matrix, we delete 2A again, but now we run into an issue where there is no degree 1 vertex. And in this case, we're kind of stuck if we're just doing our basic algorithm. And we, in the paper, give an approach for how to choose one of these edges that are causing it. It's kind of like a cycle in a hypergraph, but we delete one of the edges, in this case, B2, so to manually delete it, and then we continue with the algorithm. And when you triangulate this one, what basically happens is for each edge that you had to manually delete, you can put it at the bottom of the matrix, and you get something that's almost triangular with however many times you had to do this manual step is how far away from exactly triangular you are. So let's say we had to do this G times, and then to invert this matrix, it more or less takes time n plus G squared. And so to get good performance, we want to say that G should be very small, right? So we want to minimize G. And unfortunately, in general, you can show that this problem is in N intersect co-NP, so probably quite hard to solve. But fortunately, we show that so long as your parameters are chosen such that the matrix is sort of wide enough, have a ratio of like 1.2 or greater, then in fact, the algorithm that we present with the way to delete it that we specify in the paper, delete these extra edges, is optimal with high probability, and the size of G will be a constant. So we will have some of these bad rows, but not very many is the idea. And that's basically how we solve it. There's a bunch of additional details that I'm skipping over. This is actually a quite interesting problem to look at. And we also present many optimizations to how to make this faster and some other nice properties in the paper. So I refer to that. Okay, so let's zoom back out and let's see where we've landed. So, right, we start with a Vole correlation, and then we encode the set X as this like purple matrix, and we take the inverse. And here I'm showing the slightly more general form that I sort of glossed over. But what we compute is this de-randomization of A, which is actually this P vector. And so we encode and then we de-randomize A to get P. We send P over. The sender updates their Vole correlation with P, which is what this computation is here. And then they encode their set using their sparse matrix MY and send that back over. Here, I'm including this hash that I referred to, but this is basically just sending the encoded vector, but hashed. Oops. And then we can compute the intersection between these two encoded sets. This is just sort of what we already explained, but maybe in more general form. Yeah, and then this protocol, so let's look at how efficient this is, right? Our matrix operations were all linear, and all concretely efficient, but for communication, right, we're using the silent Vole correlation. So this takes almost no communication. Sending P is like this 1.2 parameter times security parameter times set size. So also very succinct, relatively speaking. And then these hashes can be compressed into each of size log plus 2, right? Statistical security parameter plus 2 log n bits each. So all the messages are quite small and maybe close to optimal. We also show how to compress this message a bit more, see the paper. But I guess the main takeaway here is that information theoretically, you have to send almost this many bits. You could probably shave off a few more, but we're getting close to what it's required just to communicate the sets themselves. And in fact, we're doing it with security. And yeah, we also construct, if you just delete that last message, we actually show that you end up with an OPRF. So if you have a protocol that needs an OPRF, then you could use this guy. It's quite efficient. Yeah, so we get OPRF construction. Ours is slightly different than the one I showed at the beginning in that the protocol chooses the PRF function, but that's sometimes okay. But yeah, so why did we go through all this work? Well, it's quite fast. To do a PSI of 1 million items, it takes, if you use a single thread, it takes like 0.36 seconds. If you allow multiple threads, we get down to like 0.1 seconds almost. And yeah, the communication overhead is, depending on how you parameterize things, like 251 bits per item or 180 bits of communication per item. So quite small, I'd argue. We also get malicious security for almost free. We have to increase some parameters a little bit, which adds some overhead. But yeah, we also get very good malicious security. And yeah, that's blazing fast PSI, Vole and OKBS. And I also want to mention that Visa Research is hiring. If anyone thinks this work is interesting, come check us out. So thanks. Yeah.
But you said it was NPM 12P, it should be like NPM 12P hard or something? Like,
Yeah. Yeah, I think it's hard. Yeah. I guess you didn't look at it too closely, but I remember hearing that, so I put it in the slide because it sounded cool.
Thanks for the amazing talk, Peter. I have one question. It doesn't matter anymore at that performance. Does your protocol also work for unbalanced set sizes, where you have a few thousand on one side and a million or billion on the other?
Yeah, I mean, of course you can run it, and it will still might be the best approach. But one of those messages scales with each set size. So there's two messages basically, and each one scales with your set size. So you'll still get communication proportional to the large set, which is sort of unfortunate, but the constants are very small, so this still might be the best approach.
The first message, which is big, or the second message?
They're both equal, they're by equal size. They're both like security parameter times set size. Just which direction it goes is based on which set. Yeah.
Is there, do you know of any way to like do efficient like OKDS or PSI for if you need to resist timing attacks?
Timing attacks.
Or hash-based timing attacks.
I see. You could probably, I mean, you could certainly compute a bound on how long it would take to do any one of the operations and then just like make sure you wait. I'd say that'd probably be the simplest approach as opposed to make each operation timing oblivious. Yeah, but not something I've looked at.
Okay, let's Peter for the talk. Maybe the rest of the questions you can take off.
Sure.